What is going on, everyone? Welcome back to another video. Today we're going to be doing a Fluent tutorial, the drag on the hull of a boat. Let's get into it. So in this tutorial, we're going to be analyzing the drag on the hull of a boat in order to learn how to simulate multi-phase flow within Fluent. Multi-phase flow referring to the flow with more than one fluid. In this tutorial, you'll learn how to plot the geometry in SpaceClaim that we need for this multi-phase flow analysis and how to mesh the geometry using a body of influence sizing in order to control the element sizes in areas of interest. We'll also learn how to initialize the simulation models and to implement boundary conditions for multi-phase flow. And specifically for this analysis, since we're going to be calculating the drag on the hull of a boat, we'll learn how to plot the drag plots and also plot velocity and pressure contours in CFD-Post. But before we get started, we must understand the key parameters that are at play for this analysis. The first thing that we really need to make sure is understand where the waterline of our boat is going to be, because this is going to be the interface of where the air and water meet. For this particular analysis, we can see that we have a boat here that the origin of the CAD is somewhere along the deck of the boat. However, the boat would not float that low in the water. So for this particular CAD, I'm going to say that my water line is at 400 millimeters in the negative y direction from the origin of my CAD, meaning that the air and water fluids are going to interface at this level here. And the rest of the dimensions on this sketch here are just arbitrary values in order to give enough area around the hull of my boat in order to capture the fluid behavior that will happen once the fluid interacts with our boat. And for this simulation, we're also going to be only simulating half the boat, as this will allow us to save on mesh elements and computational power, and we'll be able to mirror the results that we get over the center line of the boat. And continuing with some arbitrary dimensions, I'm going to be dimensioning the domain length to be 24,000 millimeters, as you can see here. And we're going to be placing the boat somewhere in the front half of our domain, since we are not so much interested with the flow coming into our boat, but we are much more interested in the flow around the boat and evidently any flow effects that happen off the trailing edge of our boat that we have here. The other thing that you can see from the CAD that we have here is that there are, in fact, two bodies. We have the fluid domain, which is the big rectangle around our hull, and we also have this little smaller rectangle around our boat. This prism is going to be used for the body of influence command, which will allow us to mesh smaller elements around the boat, since this is the more critical area of our analysis. And this will allow us to capture smaller details of flow behavior at the interface of the air and water, and as well as around the hull of the boat. And the elements are allowed to get bigger as they move away from the interface, since the flow behaviors are much more standardized there. And as I hinted many times, for this analysis, we're going to be analyzing multi-phase flow, where we're going to have water and air interacting with one another, air being at the top of our domain and water being at the bottom of our domain. And we're going to set a boundary condition for these fluids, and this is going to be a velocity set to 7 meters per second, which is going to simulate as if our boat was moving forward through the water and air at a speed of 7 meters per second, which is roughly equal to 25 kilometers an hour. So now that we understand the geometry that we need for this analysis and some boundary conditions as well, if we go back to the first slide, we can see the expected results that we are going to obtain. And we can see that we have a surface here that represents the top layer of the water fluid. And we can see that the fluid is coming in at some velocity and is interacting with the hull of our boat, creating some wake behind it. So now that we understand the results that we want to obtain, let's go ahead and jump into Workbench and get started on this simulation. Now with Workbench open, we can go ahead and start building this analysis. In the middle here, I have my project schematic. This is where we're going to be building the analysis with our analysis systems that we have in our toolbox on the left-hand side here. For this particular analysis, I only need one analysis system, which is my Fluid Flow Fluent analysis system. So I can drag that into my project schematic. And the first thing that I need to do is build the geometry. So I'm going to double click on geometry to launch SpaceClaim. As we can see in the bottom hand corner here, it says starting SpaceClaim. So I'll wait for that to load. Now SpaceClaim open, I can go ahead and get started with building the geometry. The first thing that I'm going to do is press on End Sketch Editing because by default, SpaceClaim has the sketching on the ZX plane. I prefer sketching on the YX plane. It just makes it easier for initialization later on. So I'm going to go ahead and press on End Sketch Editing. And the first thing that I'm going to do is open the CAD that I have for the boat. So I'm going to go ahead and use the open command here. And I'm going to search for an IGS file because that's what I saved it in. And I'm going to choose simulation boat. So as you can see, this is the CAD that I have for the boat. One thing to note is for this CAD, it is a solid body and it's not too complicated of a CAD. This is very important because we don't want too many surfaces within our CFD domain that we're going to create. A solid body is important because it allows us to more easily subtract the solid body of the boat from the solid of the CFD domain that we're about to create here. So make sure that when you're building your simulation, that your boat is not too complicated and make sure that it is a solid body because it will be much easier for the rest of your simulation going forward. So that being said, let's go ahead and continue building the rest of our CFD domain. I'm going to go ahead and press on the pencil crayon to enter sketch mode, and I'm going to go ahead and choose the YX plane. I'm going to press on the Z axis to make this normal to the screen. And now I'm going to sketch the sketch that you saw during the PowerPoint. Again, this is representing the flow around the boat, and we're only going to be sketching half the domain because we'll save on computational power and resources, and we'll be able to mirror the results over the center line of our boat. So I'm going to go ahead and choose the line selector command up here and sketch out a line from my origin to be 2,500 millimeters. I'm going to sketch a line 90 degrees to that to be 5,000 millimeters. And again, these are just some arbitrary values, again, to have enough space around my boat in order to analyze the behaviors of my fluid as it interacts with the solid body or the walls of my hull. So this is the sketch that I have here that represents my fluid domain. I can go ahead and press on End Sketch Editing to create a surface based on these curves. And the next thing that I'm going to do is pull this sketch out to create a solid body. So I'm going to go ahead and press on the pull command. And in the section here, I'm going to press on no merge. This is very important because we want to ensure that the surface that we're pulling out to create a solid body is not going to merge with the solid body of our boat. We want to create two bodies that are intersecting with one another because then we are going to go ahead and subtract the boat from the solid CFD domain. So make sure you press on no merge. And now I'm going to pull this surface out. And by holding left click always, I'm going to insert my dimension. And as you can see in the design tree here, we have two solid bodies, one representing the CFD domain and one representing the boat. So I'm going to go ahead and also drag out the back of this domain here by 18,000 millimeters, creating the overall 24,000 millimeters for my CFD domain. And as I mentioned in the PowerPoint, we want the boat to be towards the front half of our domain because we are not as interested in the flow that is coming into the domain, but rather the flow that is around our boat and especially the flow that is behind our boat so that we can analyze the behavior once the flow interacts with the hull. So now that we have our two solid bodies, I'm going to go ahead and subtract the solid boat from the CFD domain. I'm going to go ahead and use the combine command. The first thing that I need to do is click the target object. So this is the CFD domain. And using the saw, I'm going to go ahead and select the cutter tool as the solid boat that I have. And this now creates three solid bodies, one for the CFD domain, which is this one for the boat that we cut out of the CFD domain, and one for our CAD that we imported, a solid one. So I can actually select the two, or first I'm going to escape the command because we don't need it anymore. And I'm going to select my two solid bodies and actually delete these because we don't actually need these anymore. We just need the CFD domain, which is the flow around our boat. The next thing that I'm going to do is add the arbitrary body that we had around the boat, which is used for the body of influence command, which will allow us to control the size of the mesh elements around the interface of the air and water and around our boat in order to capture the smaller details of flow behavior in these areas. And this is a little bit arbitrary. There's no dimensions that we need for this. We just want to put it in the area that we are interested in. So I'm going to go ahead and enter sketch mode again by pressing on the pencil crayon and choosing my face as the face of our domain here. And by using the rectangle command, I'm going to go ahead and come outside of my domain. And I'm going to drag a rectangle out to the other side, including the boat within it. And I want to make sure that it goes beyond the confines of my CFD domain, because then I'm going to be able to extrude it. And this will allow us to be able to select the body without us having to hide bodies during the meshing stage. So this is the sketch that we need. I'm going to go ahead and press on End Sketch Editing. And by using the pull command again, and again, no merge, we don't want to merge these bodies together. We want two solid intersecting bodies. I'm going to go ahead and choose the sketches that I have by holding Control to ensure that we create one solid body that goes across the CFD domain. Press on Escape, and there you have it. We have two solid bodies, one that represents the CFD domain and one that represents some arbitrary body that is near the interface of the two fluids and around our boat for the body of influence sizing that we're going to see during the meshing stage. So that is it for the geometry for this simulation. I can go ahead and press on the big X by SpaceClaim to close SpaceClaim, and we'll return back to Workbench. So now we can see that we have a check mark beside geometry, so that is good to go. Next up is the meshing, so I'll double click on mesh, and it says starting meshing, so I'll wait for that to load. Now with the mesh are open, we can go ahead and start building the mesh for this analysis. The first thing that we're going to do is press on the plus beside connections and press on the plus beside contacts. And as you can see, since we have two bodies within our geometry here, ANSYS is reading this as two bodies that has a contact region between them. This is not totally accurate because we want to use this body as a body of influence, which is actually going to disappear during the rest of the simulation. It's going to be used to refine the elements around this midsection of the CFD domain. So we don't actually have a contact region here because these two bodies are not actually going to be intersecting with one another when we do the analysis later on. So we can actually go ahead and right click and delete this contact region. Are you sure you want to delete it? Yes, because again, these bodies are not going to be intersecting for much longer, and I'm going to go ahead and show you that right now. So for the mesh, we're going to generate the default mesh, but before we do that, we're going to add the sizing. So we're going to right click on mesh, go to insert and press on sizing. The yellow fields that we have here are fields that are missing information that need user input for ANSYS to correctly handle the sizing. So the first thing is the geometry, and the second thing is the definition or the type of sizing that we want to do. So as I mentioned, we want to do a body of influence sizing. So I'm going to go ahead and press on element size, press on the triangle that appears here, and press on body of influence. And so now we can see that we have more yellow fields here as well for our geometry and the body of influence geometry. So I'm going to go ahead and press on the body selector tool, and I'm going to choose the body of the CFD domain. This is going to be the scope geometry. So I'm going to go ahead and press on no selection, press on apply. So I've applied one body, which is the CFD domain, to the geometry of the scope. And for the body of influence, this is going to be the body that is intersecting right around the interface of our two fluids and around our boat. So I'm going to go ahead and with the body selector tool, select this body, and I'm going to apply this to the body of influence by pressing on no selection and pressing on apply. So now one body has been added to the body of influence. By default, it says here that the element sizes are going to be 1.3145 meters, which is going to create pretty large elements for this mesh. I'm going to go ahead and change this to 0.2 meters. And now we have a check mark beside body sizing. So I'm going to go ahead and generate the mesh based on this sizing. So right click on mesh and press on generate mesh. And we can see that the mesh has been generated for this geometry. A couple things to note here. One is that the body that we had here before when we had connections or an interface, that body has actually disappeared, as I mentioned before, because it was going to be used for the body of influence. So it's not actually going to be interfering with the domain or with our CFD domain, I should mention. And this body has allowed us to refine the elements right along this interface here and around our boat. And had we not done this body of influence sizing, the elements would be just as large as the elements near the bottom and top of our domain. And again, we can afford for the elements to be bigger at the top and bottom because we are less interested. There's less changes in the flow behavior at these regions, but there is more change right around the boat. So this is where we want smaller elements in order to capture the smaller flow behaviors. So now with our mesh created, we can also go ahead and add some name selections. These are going to allow us to better implement the boundary conditions when we move on to the Fluent stage. So I'm going to go ahead and press on the face selector tool, and I'm going to choose the front of my face near the bow of my boat. And I'm going to right click and press on create name selection, and I'm going to name this the inlet. I'm going to go to the back and do the same for the outlet. Create name selection and press or type outlet. And I'm going to select the three faces that we have here in the middle of our geometry when we are going to mirror it. So I'm going to right click and press on create name selection. And this is going to be called symmetry because again, we're going to mirror it over this plane when we get the results. And lastly, but probably the most important, is the wall of our boat or the hull. And so I'm going to go ahead with the face selector tool. I'm going to select all of the faces. Actually, we need to hide this geometry because it is interfering with me choosing the faces of the hull of the boat. So I can right click and press on hide. Whoops, that was the wrong one. I wanted to hide that body and show this one. So now if I choose the face selector command, I can choose the faces of the hull of my boat. So now with all of the faces selected, I can go ahead and right click and press on create name selection and name this hull because it's the hull of my boat. And this is going to be set to a wall when we move on to Fluent. And you can imagine that if you didn't use a solid body for your boat that you have here, you would have so many more faces. Even my boat is a little detailed with the chamfers that it has, but this would be much, much harder if I had a much more detailed boat or one that was not a solid body. But that will be it for the name selections for this geometry. So now that we've created the mesh for this analysis and the name selections for the inlet, outlet, symmetry, and the wall of the boat, we can go ahead and press on the big X to end the mesher and return back to Workbench so we can actually launch Fluent. And when we return back to Workbench, we can see that we have a lightning bolt beside mesh. What does this mean? Well, we created name selections after we did the meshing stage. So these name selections weren't transferred through the module to the setup of the program. We just need to update the mesh module. So I'm going to go ahead and right click on mesh and press on update. And now you can see we have a check mark beside mesh, meaning that all the information that we created during the meshing stage was transferred to the setup in Fluent. So now we can go ahead and initialize the simulation model and implement boundary conditions and actually run the simulation. Very exciting. So let's go ahead and double click on setup to launch Fluent. So before entering Fluent, we're met with the Fluent launcher, which here it's just asking us to reserve essentially computational resources. The only thing that we need to do here is for solver processes. On my local machine that I'm running ANSYS on, I can put the solver processes to 2, and in parallel settings, I can put solver GPUs to 1. But these are pretty generic settings for any computer that you're going to run ANSYS on, and this just allows Fluent to access more computational resources within your computer, essentially allowing your simulation to run a little faster or to solve the results a little faster. So that's the only thing that we need to change in the Fluent launcher. So I'm going to go ahead and press on start to launch Fluent. So in the bottom left-hand corner here, it says starting Fluent. So I'll wait for that to load. Now with Fluent open, we can go ahead and start initializing the simulation model. But the first thing that I'm going to do before that is in the mesh section here, I'm going to go ahead and press on make polyhedra. And what this is going to do is convert the triangular elements that we had in our mesh into hexagonal elements. This is going to serve a couple advantages for us in this simulation. Mainly, it's going to improve simulation accuracy and speed, since hexagonal elements have more faces to them, which leads to better approximation of the geometry and the flow field. And this is also going to allow us to reduce the memory and the computational requirements that we need for the simulation, because the hexagonal elements are going to cover larger volume and require fewer elements than the triangular elements would, saving on memory and computational time for this analysis. So I'm going to go ahead and press on make polyhedra, and it's going to write stuff to the console window. We can see that in the console window it says done. So let's go ahead and display the mesh that has been created. So we'll go ahead and press on the display button here. And we're going to display the edges and faces and press on display. So as you can see in the viewing window here, instead of a whole bunch of triangular elements, we have hexagonal elements instead. So it's replaced all of the triangular elements with hexagonal elements. And again, this is going to allow for improved solution accuracy and speed and reduce the computational requirements that we need for this simulation. Very cool. So let's go ahead and press on the close here for this window. And the next thing that we need to do is implement the gravity, because we have two phases of fluids. So we need to understand how these are going to interact with one another. And since my geometry here is built on the ZX plane and my Y direction is the upward direction, this is going to be how I implement the gravity. So it's going to be in the negative Y direction for negative 9.81 meters per second. And in models, I can go ahead and double click on models. And for the viscous model, we can see that we have the K omega model. This is going to be good for this simulation. And in multi-phase here, it says off. That is not good, because we do want multi-phase flow in our simulation. So I'm going to double click on multi-phase. This is going to open up this window here. So instead of off, we're going to go ahead and press on the volume of fluid for homogeneous models. And it's going to open up this window here. And we're also going to check mark the box here beside open channel flow and implicit body force. So I'm going to go ahead and press on apply and close this window. And the next thing that we have to do is add the other materials, because by default, if we double click on materials, we can see that ANSYS or Fluent only has air. So if we double click on air, we can see that this opens up this window here. These are the properties for air within ANSYS. And if we wanted to add other materials, we could go ahead and press on the Fluent database button. And this would open up this window here. And these are all the fluids that are available to us within Fluent. But we are particularly interested in the water liquid fluid that has these properties here. So we can copy this to our project by pressing on copy. And now we can close this window, and we can close this window. And if we press on the plus, we can see that water liquid has been added to the setup tree here. The next thing that we need to do is actually return to the model here. So we'll double click on model and return to multi-phase, because in phases here, we now need to initialize the material for each of these phases. So we have phase 1, which is air, which is good. And we have phase 2, which is air, which is not good. We want water instead. So we'll press on the triangle here and press on water and press on apply. So now water has been added to phase 2 and air is the material for phase 1. So I'm going to go ahead and press on close. So that is good to go for our phases. Next up is the boundary conditions. So if I double click on boundary conditions, we can see this is where we have the name selections that were created during the meshing stage. We have the hull, which is a wall, so that is good. We have the inlet, which by default is a velocity inlet. We're going to initialize this as a pressure inlet instead. And this is going to open up this window here. We're going to leave this all the same, but in the multi-phase tab that we have here, we're going to press on the check box beside open channel. And this is where the water line of the boat becomes very, very, very important. We see here that we have the free surface level. This is going to represent where the interface between the two phases of fluids are going to be. And since the water line represents where the water comes up to on a boat, the water line is the free surface level for this simulation. And in the PowerPoint, I said that my water level for my boat was going to be at negative 400 millimeters, which is actually equal to 0.4 because it's meters here. And again, this was a number picked so that I could have a water line that resembled what a water line would look on for the CAD of this boat. So if you have your origin of your CAD at the water line of your boat, you would put 0 for the surface level. And depending on where you want the waterline on your boat, this is where you would change this value here. Next up is the velocity magnitude. This is going to represent the velocity of our fluid that is entering our domain, which again simulates as if the boat was moving forward through water that was not moving. So I'm going to initialize this to be 7 meters per second as per the PowerPoint at the beginning of the video. And finally, the bottom level here, this represents the bottom to where the second phase starts. So we have the second phase from the bottom here all the way up to my water line. So as I showed during the sketching phase, during the building of this geometry, I sketched to have the end of my domain here to be at negative 4.5 meters or 4,500 millimeters. Again, representing the bottom level of phase 2, which phase 2 is the water liquid phase of my simulation. So I can go ahead and press on apply to implement all of these changes for the pressure inlet. And I can press on close. And next up is the same thing for the outlet. So if I click on outlet, we can see it's a pressure outlet. So that is good. And we want to implement the same conditions here. So in multi-phase, we're going to press on the check mark by open channel. And we are going for free surface level, we're going to implement these same values. Free surface level being the interface between the air and water, and bottom level being the bottom of the fluid domain, or the water domain, I should say. Press on apply, and we can now close this window. And if we go ahead and press on symmetry, we can see that the type is symmetry, so that is good to go for our boundary conditions. Next up is the reference values. So if we double click on reference values, we're going to compute the reference values from the inlet. And this is just going to change the velocity, viscosity, and density based on the parameters for materials and boundary conditions that we put into place for this simulation. So that is it for the setup of the program. We can go ahead and move on to the solution part of this tree. So if we double click on methods, we can see that the scheme that we're using is the coupled method. This is a good and simple scheme, so we're going to leave it as is. In report definitions, or in monitors, sorry, if we press on monitors and double click on residuals, we can go ahead and see the residuals that we are playing with for this simulation. And we can see the absolute criteria for this simulation is 0.001. We're going to leave this as is. We're not going to try to achieve more accurate results than this, because this is going to be already very accurate by itself. So we're going to leave the residual monitors as is. And the next thing that we're going to go do is implement the report files that we need in order to calculate the drag on the hull of the boat. So if I double click on report plots, it's going to open up this window here. And if I press on new, it's going to open up this window here. And if I press on new again, now I can initialize a report definition. So if I go to force report and press on drag, this is going to open up this window here. And I can name this to drag just so I know what report definition this is. And we're going to be calculating the drag force on the hull of the boat. So make sure that you calculate, or that you press on hull, sorry. And for the force vector, so based on the orientation of your geometry, this could change for you. But I have my gravity in the y direction, and in the x direction, I have the width of my domain, and I have my fluid coming at me in the z direction. So it's logical to say that the drag would also be in the z direction, because it's going to be withstanding the flow that is coming at it in the z direction. So for the force vector for drag, instead of having a 1 in the X direction, we're going to have a 1 in the Z direction, again, based on the orientation of my particular geometry and how my fluid is interacting with my boat. And we're going to go ahead and press on the checkbox beside print console, which is just going to print the results as it goes through the iteration of calculations when solving the simulation. So I can go ahead and press on OK. I can press on OK here and close this. So if we press on the plus beside report plots, we can see that we have now a drag plot that is going to be plotted to the screen when it does the calculations. So that is it for report plots and residuals. So now we can go ahead and initialize the simulation model. So if I double click on initialize, we're going to do standard initialization, and I'm going to compute this from the inlet. And for the open channel initialization method, I'm going to set this to flat. And I'm going to press on initialize. Now the simulation has been initialized, and we can see what the initial guess was. So if we go ahead in results here, press on the plus and right click on contours and press on new. And when it says contours of, we're going to go ahead and go down to phases. And we're going to put the volume fraction of phase 2. And we're going to press on the hull inlet outlet symmetry and the wall solid. Press on save and display. And now we can see the phases within our CFD domain. So the blue phase being the air phase and the red phase being the water phase. And we can see the interface between them along the waterline of our boat here. So this is the initial guess that it's going to be using for this analysis. So we can go ahead and close the contour. And now that we've initialized the model, we can actually go ahead and run the simulation model as well. So if we go ahead and press on run calculation, double click on run calculation, sorry. For the time scale factor here, we're going to implement 0.5. This is a very standard time scale factor for CFD simulations in order to ensure that the simulation is going to remain stable and accurately capture any transient behaviors in flow that would occur. And for the number of iterations here, I'm going to put this to 1,000. And if it reaches the residuals that we implemented or that were set by default in ANSYS, it will actually terminate itself once it reaches below these residuals. But we'll implement 1,000 in case it runs through all 1,000 of these iterations, but it should be more than enough. So now with these in place, we can actually go ahead and press on calculate, and it's going to start plotting some information to the window here, start plotting all the iterative calculations that it is doing. So I'm not going to bore you guys with it solving the iterative calculations with the magic of editing. I'm just going to cut to when it is done solving the simulation model. But before I do, as you can see here, it started plotting the drag graph based on the information or the calculations that it's doing since we press on the print to console checkbox beside the report definition for drag. But now that it's calculating, I'm going to go ahead and cut to when it is finished, just so you guys don't have to sit through all the calculations. Hey guys, welcome back. As we can see, we have a text box on our screen here that says calculation complete. So we can go ahead and view the results that we've gotten. Let's go ahead and press on OK beside calculation complete. And if we scroll up in the console window here, we can see that the solution actually converged after only 178 iterations. So that is a very good result. If we go ahead and press on these scaled residuals, we can see that all the residuals drop below the accuracy of 1e to the -3 that we were monitoring. For the 1,000 iterations that we were going to run this simulation for, we could actually go ahead and try to achieve the better accuracy of 1e to the -6, but 1e to the -3 is a fairly accurate result in its own right. So let's go ahead and just stick with the results that we've obtained for now. And if we press on drag plot, we can see, again, a similar story at the beginning when the residuals were very big. It had a hard time estimating what the drag was going to be, but then it plateaued over time until it reached its final value. So this is all good information to know, but we can also go ahead and visualize the results that we've gotten. So let's go ahead and close Fluent by pressing on the big X and pressing on OK to close Fluent. And let's return back to Workbench. And we'll double click on results to launch CFD-Post. So it says starting CFD-Post in the bottom here. And it's already loaded. So let's go ahead and visualize the results that we've obtained. The first thing that we're going to do is make sure that hull is selected here. So select hull so that we can see the solid body of our boat. And we're going to deselect wireframe so that we don't have that nasty wireframe from impairing the visualizing of the results. And we're also going to double click on FFF solid here, and we're going to apply the reflection across the ZY plane. So press on apply, and now we can see that our model boat has been mirrored across the ZY plane. So we're going to be able to analyze the flow across both sides of the boat, even though we only calculated it around one side of the boat. So the next thing that we're going to do is add an ISO surface. So let's go to location and press on ISO surface. And this will allow us to create a surface of our fluid domain at the water level or the free surface level in our CFD domain. So let's go ahead and press on OK beside ISO surface 1. And for the variable definition, we're going to change this to the phase 2 volume fraction. And we're going to set this value to 0.5. And we're going to press on apply. And you can see that an ISO surface has been created based on the information that it has for the second phase of our simulation, which is our fluid phase. So this is the ISO surface at water level, at the water line of our boat, as you can see if I put it to a more straight on angle here. And we can also see from this ISO surface, we can see that the water or the liquid is calm at the front of the boat, and as it hits the boat or as it impacts the boat, we can see that there is a wave that is created due to the interaction between the water and the hull of the boat. And we can see that there is a wake behind the boat as it is moving through the water, which is an expected result and a result that we see when boats move through water. So this is a fairly good result. We could also go ahead and visualize the velocity vectors. So let's go ahead and press on the vector button up here and press on OK. And for the location of this vector, I'm going to use the ISO surface. So it's going to plot the direction of the velocity of the fluid. And let's go ahead and press on apply. And we can see that we have a whole bunch of arrows. They're a little hard to see right now. So we'll reduce the number of arrows by increasing this factor to 10. And in symbol size here, we'll use a 3D arrowhead because it'll be easier to see, and we'll make the arrowhead a little bigger. So if we press on apply, there we go. Now we can see that we have slightly bigger arrows. They're still a little hard to see based on the color of the two surfaces because they're appearing as both green. So we can also change the color here by using a different color map. So if we use like divergent cool here, now we have pink arrows. So you could go ahead and play with the size of the arrows and the colors of your ISO surface and your velocity vectors in order to create something that is a little more visually appealing or a little more easy to see. But based on this information, with the velocity vectors, it tells a similar story. We can see that the velocity is, or the fluid, I should say, is headed towards the boat at 7 meters per second, which is representing our inlet condition. And it is impacting the boat, causing the water to diverge and creating a bit of a bulge or a wake along the hull of the boat, which is followed by a valley between the two wakes or the two waves that are being created. And this creates a triangular wake behind the boat, which again is a very physical result and is a result that we see as boats move through water. So we can say that the results that we've obtained are fairly good. The other thing that we can go ahead and do is in the calculators here, we can go ahead and calculate the drag force on the hull of the boat based on the fluid moving at this velocity. So if we go ahead, press on function calculator, double click on function calculator, sorry, and for the function, I'm going to put in the force and the location is going to be hull. So if I go ahead and press on calculate, we can see that the force on the hull of the boat was calculated to be 4,604 newtons. And this value is pretty high because the boat is moving fairly fast through the water, as we can tell by the velocity vectors and the wake that's being created at the bow of the boat here. And we would be able to do a proper results validation by decreasing the fluid velocity and viewing what the force or drag force would be due to decreasing or increasing the velocity of the fluid, and plotting a chart based on the drag force versus the fluid velocity or the boat velocity, because that is the same. In a CFD simulation, we are simulating as if the flow is moving towards a stationary boat, but in real life, this would not be this is not what's actually happening. What's happening is that the boat is moving through stationary water. But I'll let you guys explore what the drag would be on the hull of your boats based on your boundary conditions that you'll input for your multi-phase flow. So that will be it for this tutorial on how to do a multi-phase flow analysis within Fluent, particularly to simulate the drag on the hull of a boat. Don't forget to like the video if you guys thought it was helpful, and subscribe for more engineering content.